Hello there. Today we're going to talk about identities. What exactly is an identity? Well, in the world of math, an identity is where two things are equal to each other. Like x equals 2? No. Like 2 plus 2 equals 4? No. It's when two things that both could be unknown are equivalent to each other. So, for example, 2x plus 2x equals 4x. Now that is an identity. Boring, but it's an identity. The more interesting things have to do when two things that are different from each other are equivalent. Or when you can write something in a different way that makes it more interesting. And why do I want to talk about identities? Because this gives me a chance to show you my favorite identities. So I'm going to show you 4 of my favorite identities today. The reason they're my favorites is because I derived them myself. Not that I thought of them the first time. No, these are well-known things, but these are things that I had worked out, and so they're interesting to me. And if you don't care about that, that's fine. So, first of all, you know how when you're trying to convert between Celsius and Fahrenheit and you have to do all that weird stuff with the 32s and all that crap? Well, that's not necessarily necessary. What I found a long time ago is that you can always use 40s. Negative 40 is the same in Celsius and Fahrenheit. So if you just convert your temperature to 0 and multiply by a change factor and convert it back from 0. So here's what I mean. Take the Celsius temperature, say it's 20. Add 40 to it, right? That gives you 60. Divide by 5. That gives you 12. Multiply by 9 is 108. Subtract 40 and that's 68. And the Fahrenheit temperature is 68. And by the way, that's correct. You can do it the other way. Say your Fahrenheit temperature is 32. Add 40 to it, that's 72. Divide by 9, that's 8. Divide by 5, that's 40. Minus 40 is 0, which is also correct. So you see how it works. And that is simple. And all you have to do is remember it, like from bigger to smaller, smaller to bigger. You don't have to worry about that 32 crap. Now you always do the same thing. You add 40, subtract 40. So I always thought that was easier. And that is my first favorite identity. My second favorite identity is one that I used in a previous video. It is the sine of 5x. Now this is, you could just say, well, that's really just a calculation, but no, it's really useful in that proof, as you've seen if you've watched that video. Sine of 5x is this number here. The cosine is this number here. And what's cool about these numbers is they're the same. You see the 5, the 10, and the 1 coefficients. So what this is this row of the Pascal triangle. And you'll find that all of these sine of and x are like this. And that's pretty cool, actually. It takes, so like with 4, you get these come to sine and these come to cosine. You just have to alternate the signs. So that's really pretty cool. And the alternating signs comes from, when you, well, I don't know how to explain that very well. It has something to do with the derivative. Anyway, that's number 2, the sine of 5x. My number 3 favorite identity is something that I found a while ago when I was playing with power. So most people play with squares, right? And they find all the weird things about squares. Well, I play with cubes and force, so nothing too interesting with force. And then I'll come back to cubes later. Then I got to fifths, and I noticed something interesting. Take a look at this column, and then take a look at this column. They're the same. So this is actually my third favorite identity, which is that if you raise any number to the 5th power, the last digit remains the same. Isn't that cool? I think that's pretty cool. It also tells you some interesting things about how numbers work. Just if you think if the last one's the same, then shouldn't the 4th one be 1? Well, no. Sometimes it's 1, sometimes it's 0, sometimes it's 6, sometimes it's 5. When you raise the 4th power. It's just that they all work out. So the fifth power is the same as the first power. Hey there, let's talk about my favorite math identity. Why is this my favorite? Well, first of all, because I sort of uncovered it when I was much younger. I had read some stuff about adding squares together and weird things like if you have 4 squares, you can get any number and things like that. And I wondered what would happen if I started adding cubes, and as it turned out, an interesting little pattern appeared. Now, I did not discover this, I did not invent it, but it was cool because I hadn't seen it before. So what happens when you add cubes together? Well, you add 1, you get 1. You add 1 and 8, you get 9. You add 1 and 8, which is 9, plus the next cube, which is 27, you get 36. And I start to see a pattern over here. But if I add 36 and the next number, which is 64, you get 100. And one more time, if you add 100, and you add the next cube number after 64, which is 125, you get 225. And I think I'll stop there because he's getting higher than my brain can handle. The point here is the numbers on the right, they're all squares. So what are they squares of? Well, let's take a look. 1, and then the next one is 9. 9 is square of 3. And then the next one is a square of 6. Okay, and the next one is the square of 10, and the square of 15. So what are these numbers? Well, I know what they are, but if you look really closely at the difference between these numbers, the difference between 1 and 3 is 2, the difference between 3 and 10. The difference between 1 and 3 is 2, the difference between 3 and 6 is 3, the difference between 6 and 4 is 6 and 10 is 4. Okay, so 2, 3, 4, 5, 6, and if you added 0 at the top, you'd have 1, 2, 3, 4. Well, that looks like a pretty standard pattern there. And one thing about differences is, if you do it again, they're all the same, right? They're all 1, 1, 1, 1, 1, 1, 1, 1, which means this series 1, 3, 6, 10, 15, that is a square function of some sort. And you may already realize this is a triangle numbers. So what I found is, what other people certainly found way before I did, is that if you take all of the cubes from 1 up to n and you add them together, the result will be some triangle number squared. And it turns out that triangle number is the same triangle number as the highest cube you added. So its formula looks like this: the sum of the cubes from 1 to n is equal to the triangle number of n. You show it this way, or this way, if you like sum notation, or this weird graphical way that I like. Now, this is interesting because this doesn't work with anything else. It only works with triangle numbers. Now, there was a really good methodology video that covered more general terms of this, and it was fantastic, and I can't do that. I'm not that good at these things. But this has some interesting sort of side stuff to it. So what I can do is I can show you a couple ways to show this, a couple of proof, well, at least one proof, and I can give you sort of the idea behind why this might work. So here's a visualization of kind of what's going on. If we take 1, we put it in this corner, and we're going to add on 8. Well, what's 8? It's 2 times 4, right? So if we take 2 by 2 square, put it here, and then divide the second 2 by 2 square in half and stick it here and here, we've added 8, and now we get a square again with sides 1 plus 2, which is 3, which is 9. So we've got 3 squared. Alright, if we do it again, and we take, now we need 3 times 3 squared, which which is 3 plus 3 plus 3, right? We put the Q square here, we stick the other two squares here and here. Do the same thing with 4, but now we need 4 squares of 4. So we take one square, put it here, take the other two, put them there, and then we've got this last square doesn't fit, so we cut it in half again and stick it there, and magically it fits. And now we've got 1 plus 2 plus 3 plus 4 squared, which is 100. And you can do it with 5, and again, 5 of them fit evenly. Interesting things going on here. You'll see there's a pattern of every even one you have to divide in 2. But also this identity, which should be obvious, is that when you when you cube, it's that number times the square. So that's kind of obvious, but that's what you're seeing here, is you go up by 1 each time. So you're going to have room for just one more. And the sides are growing by the numbers, so you're getting the triangle number. That's how that works. Now, if you prefer algebra, here's the algebraic proof. Basically, you need to prove it by induction. So you see that the first one works, right? If you 1 equals 1, and you see it for the second case. If you square, you see it for the first few cases. So obviously it works. So in algebra, how would you prove this? Well, you prove by induction that the first case works, which we kind of did. And then you prove that we go from one step to the next, it works. So what we're going to do is we're going to take we're going to compare the triangle numbers from n to n plus 1 and see what the difference is, and see if that difference is the same as the sum of the cubes difference. So they should both go up by the same amount. So one thing we can do is triangle numbers have this neat little formula. So we can use this formula to show the difference. First, the triangle number of n is n plus 1 times n over 2, and if we square that, we get this formula. Then if we go up 1, we just add 1 to n plus 1 and add 1 to n, and we do this arithmetic, and we get this formula. Then what we do is if we subtract the t of n squared from t of n plus 1 squared, and the result is this number. So how does that relate? Well, what's the difference between one cube and the next? Well, what's the cube of n plus 1? It's this formula here. So what's the difference between n cubed and n plus 1 cubed? It's this 3 terms right here. These 3 terms look a lot like these 3 terms over here, don't they? So there is your proof. The differences are the same. So each time you go up 1, you're adding the same amount. That's why it works. And this is actually rigorous because it's proof by induction.